Hello, and welcome to the second video in this series. I just want to quick go over what we're going to be talking about again. Here are the outlines and objectives. The numbers represent the videos, so we're on video 2, so we're going to be talking about spectral phase. But before I go into video 2, I want to do a quick recap of video 1 so you can see what we've talked about in the past. So in video 1, we took this diagram here, which just shows wave interference, right? And we extended this to all the waves of a laser, and we got this diagram here. And this diagram ended up being useful because it can encode certain things. So for example, it can encode the intensity spectrum by saying at each wavelength, because the y-axis is wavelength, how wavy is each wave? What is the amplitude of each wavelength? And the amplitude of each wave corresponds to the intensity at that wavelength. So you can encode the intensity spectrum in that way. And you can also encode the pulse by adding up all the waves, just like we did in the first diagram here. We just added these two to get this. You can do the same thing here. You add up all these waves to get the net, and that ends up being the pulse. And then we can encode the phase by saying from transform limited, how much do you shift each wave? And you can represent that by these dots. Then we wanted to write this in sort of an equation form. So first we said, okay, we want to plot a bunch of waves. So we use e to the I omega t, and we get a diagram that looks like this. And then we wanted to control the phase, so we did minus I phi of omega to get control of the phase. And then we added an e of omega up front to adjust the amplitude. And then we added an integral sign to sum up all of the waves as if they were interfering to get the pulse. If you want any more detail than that, you have to go to video 1, but that was just a quick recap as to what we talked about. So in this video, I'm going to talk all about spectral phase. This whole thing is going to be about phase. And so the general question is, how can we use the representation? Because I went through all this effort to introduce this representation. Obviously, I'm going to use it because I find it useful. And I want to use that kind of representation to say, why does a certain spectral phase lead to a certain electric field? Because a lot of things like, for example, a linear phase shifts a pulse in time, or a second order phase does this, or so on and so forth. I want to use the representation to explain why these certain phases lead to these electric fields. And that's the general idea of this entire video, is why does a certain spectral phase lead to that electric field? So talking about spectral phase, I have to show a phase spectrum, obviously. So here's an example of a phase spectrum. I showed this in video 1. And what is it saying? Well, the x-axis is wavelength, and the y-axis is phase. And what is it saying? Well, it's saying, okay, well, you take your 650 nanometer waves, and you shift them by, it's off the graph, but I'm assuming it's 200 radians, for example. Then you take your 700 nanometer waves and shift them by, 20 radians. And take your 800s and you shift them by 0 radians, so you leave them alone. And then you shift your 900s the other way by however many. So basically the y-axis tells you how much do you shift each wave in terms of radians, and the x-axis tells you which waves you're shifting. And in the first video I talked about how you're shifting from transform limited. So you take a transform limited pulse, and then you shift your 800s by blank, shift your 700s by blank, and so on and so forth. So this kind of shows like a transformation from transform limited to whatever pulse you're going to get. So when we talk about phase, we normally talk about it in terms of angular frequency. I'm aware that for this graph here, it's in terms of wavelength. You'd expect this to be phi of lambda. But normally when we talk about phase, we talk about it in terms of angular frequency. So we normally say phi of omega. And I'm just going to keep on doing that. And notice that they're interchangeable. I just want to note that if you did this in terms of angular frequency, this graph would be very different. But you can change between them. So they are interchangeable. You just have to do the equation from lambda to angular frequency. So when you talk about phase, we normally talk about it like this. And let's just play around with it. We're going to see what we can do just playing around a little bit. So if you remember from your Calculus 2 class, we can take a Taylor series. So Taylor series basically expands a function, certain types of functions, in terms of their derivatives. And so you can get this. And notice how when we take a Taylor expansion, we take it about a certain point. Right? So you can do a Taylor expansion about 0. That's a Maclaurin series, if I remember correctly. And so that's in this equation, it's point A. So you can choose A. This gives us a degree of freedom as to what point do we want to center our Taylor expansion about. And so let's take a Taylor expansion, but we have to choose what point we want to do it about. And so I have no good ideas. I'm sure you don't either. So let's just choose point A. Let's just do 0. Right? So we're going to set A equal to 0. So we're going to do a Taylor expansion about 0 because there's no other good ideas, is there? So let's try that. So we're going to do a Taylor expansion of the phase about 0. And why are we doing this? We just want to, it ends up being useful in the end. And why is that? Because you can expand in terms of the derivatives, and then you can change certain orders. So for example, if I want to add first order, you just change the first, the linear part of the Taylor expansion. If you want to add second order, you just change the second order part. This, it's kind of flimsy. If you want to just change the parts, then it's useful to kind of expand it out and then change the certain parts and then put it back together, so to speak. But I'll show that in a second. So we're going to do a Taylor expansion of the phase about 0. And if you do that, you get this. So phi of omega, and this is an infinite sum, phi of omega is phi 0 divided by 0 factorial plus so on and so forth. We can clean this up a little bit by noticing that each of these terms, there's sort of a constant term for every single term in this series, right? So phi 0 divided by 0 factorial, phi prime of 0 divided by 1 factorial, these are constants. So we just redefine it. So we just say, we take all the constant terms and we just redefine them as big phi sub blank. So for example, big phi sub n is the nth derivative at 0 divided by n factorial. Right? So you can just clean these up. So the third derivative is the third derivative at 0 divided by 3 factorial, and that's just set as big phi of 3. Right? So you just sort of clean it up. So if you were to change big phi of 3, you know in your head that you're actually changing the third derivative at 0 divided by 3 factorial. That's the general idea. So that's that. That's nice. But let's see what else we can do. Can we choose another A? Well, a sort of intuitive choice of this would be, well, we want to do a Taylor expansion, so it makes sense to kind of do it at the center of our spectrum. And what's the center of our spectrum? That's phi naught. I'm sorry, omega naught. So it's omega naught is the central angular frequency, so it'd be at the center of our spectrum. And it makes sense to kind of choose that point to do the Taylor expansion about the center, because that's the part where we care about, right? So we can do a Taylor expansion about omega naught. That's another choice that we can do, and we can see what we get here. So if we try that, you get this. A little bit more complicated because you have this x minus a, so it's omega minus omega naught. But again, we pull the same trick. We take all these constant terms and we redefine them. Right? So we just change that. So now we can say phi naught is phi of omega naught divided by 0 factorial. Phi of 1 is phi prime of omega naught divided by 1 factorial, so on and so forth. So phi sub n is the nth derivative at omega naught divided by n factorial. And so now we have these two expansions, right? So we have one in terms of 0. One is a Taylor expansion about 0, and the other is a Taylor expansion about omega naught. And we get these two different choices. And it turns out that these are the only two that people really talk about. They actually only talk about omega naught, but these are the two natural choices, and there's no other really natural choice to do. So we have these two. And you know, I'm not going to choose between them now. I'm going to choose between them in a second. But now let's talk about each term. Right? So now we have this 0th order term, right? These constant terms. Then we have a linear term. Then we have a second order term, and so on and so forth. And now you should be able to kind of see why this is useful. Is we have control over these phis, because we know that big phi sub 1 is just the first derivative at 0 divided by 1 factorial. So since we have the control over the first derivative at 0 or the first derivative at omega naught, for example, we can change these phis. So for example, if I wanted to isolate phi 1, we can set all these equal to 0, except phi 1, and then change that and see what it does. So we can just sort of add like it's like a recipe, like add some second order, add some third order, and so on. And this actually ends up being very useful. So now let's talk about each component. So we're going to start with the 0th order component. That's just the constant term. So what we're going to do is we're going to set all these phis equal to 0, except phi naught, except the two phi naughts, and see what they do. Choose one. So let's just choose the omega naught term, because that's the one we're going to go with. So we have this Taylor expansion of the phase, and we're going to talk about the 0th order component, which is just this part. So we're going to set everything else equal to 0, and we get phi of omega is equal to omega naught. And now let's change omega naught and see what we get. So if we change omega naught and we do our wave representation, we get this. So as you can see, as you change omega naught, you sort of get this thing. And notice how it's curved. Notice how, not it's curved, but it has a slope to it. Notice how it's kind of going like this. It's kind of following the waves. Now that shouldn't actually be that intuitive, because if you remember, this is the phase spectrum. So if you have it as a constant, you'd expect a straight line just moving, right? Like, because if you have y equals 1, it's a straight line. Same here. It's actually weird that it's kind of curved, but let's think about why that is. Well, let's say phi naught is equal to 2 pi. So how much do you shift 940 nanometers? Oh, well, you shift it by 2 pi radians, so that's 940 nanometers. So you shift the 940 nanometers by 940 nanometers. And then when phi naught is equal to 2 pi, how much do you shift your 800 nanometers? Well, you don't shift them by 940 nanometers, you shift them by 800 nanometers, by one wavelength. So when phi naught is equal to 2 pi, you shift each wavelength by that wavelength. So for example, when it's 2 pi, you shift the 940 nanometers by 940 nanometers. So if they're here, they get shifted all the way out here. But if you're at 680 and it's 2 pi, you shift it by 680 nanometers. You don't shift it as far as the high ones. So in a sense, I understand that phi of omega is constant, but since it's constant, the constant is actually with each wavelength. So you shift with respect to each wavelength that you're shifting, if that makes sense. So for example, when this is 2 pi, 940 nanometers gets shifted by one wavelength of 940. 800 gets shifted by one wavelength of 800, and so on and so forth. So that's kind of a subtlety, is when we talk about phase, the number that you get out on this side is applied to each wavelength, so with respect to each wavelength. And so that's why this is actually kind of sloped. But what does it really do? Well, here I'm applying the same thing. I'm just changing phi naught, and I'm looking at the pulse. And as you can see, what's really happening is the pulse is kind of like the waves are kind of shifting along here. But notice how the overall pulse is kind of staying in the same spot. Right? The envelope of the pulse is kind of constant, but just the waves inside the pulse are shifting. And so you can see, like, at this point, at time 0, the electric field is positive, and at some other phi naught, it's negative at time 0. So you're just kind of shifting, that's why they call this the absolute phase. It's just the phase of the waves within the envelope of the pulse. And I have pictures showing that here. So for example, here is kind of a larger pulse with phi of omega is equal to 0, and here's the same pulse with phi of omega is equal to pi. What is happening is you've shifted the phase of the waves by pi, and you can see at time 0, it's kind of hard to see, it has a peak at time 0, but when you add pi as the absolute phase, it's actually negative at time 0. So you've kind of flipped at time 0, what once was positive was now negative. So you just, and notice how the envelope of the phase, the overall pulse looks the exact same. It's just that you've shifted the phase of the waves within this envelope. And here's, for example, for a shorter pulse, phi of omega is equal to 0. You can see you have a huge peak at time 0, and then we have phi of omega is equal to pi. You've shifted the phase, and now that big spike in electric field is now negative. And you think if you apply pi, it would go back up. So, and now notice how the envelope is all the same. It's just that you've changed the phase within the envelope. And another intuitive point to make is that clearly it affects smaller pulses more, importantly than big pulses. So big pulses, you can't even tell between these two. The small one is extremely important. So if you had a charged particle in this electric field, it would act very differently if you had a charged particle in this electric field. This one would be shot one way, this one would be shot the other way, because the huge spike at time 0 is different. So that's sort of an intuition, and that's a fun little fact, is that it's more important for smaller pulses. So now let's talk about linear phase. So that was the constant term. All we know is that it just shifts the phase of the waves within the pulse. Fine. So now let's talk about the linear term. And now let's notice, now these two expansions are no longer the same, right? They weren't the same in the first one, but they have a big difference. It's omega minus omega naught versus just omega. And so now we have to choose between these two representations. So we're going to compare the two and see which one we like more, which one is going to be more useful to us. So we're going to set all the phis equal to 0, except the linear terms, and we're just going to change phi 1 from minus 5 to 5 and the other phi 1 from minus 5 to 5, and compare them and see which one will be more useful to us in the future. Right? So if we do that, let's start with centered at 0, the Taylor expansion centered at 0. If you do that, you get this. So we know that the Taylor expansion, everything cancels, and you can just get phi of omega is equal to big phi of 1 times omega. And we're just changing phi 1 from minus 5 to 5, and we get this. Now, if you've been following along, that doesn't actually make sense at all, because you have this linear thing, and you're changing the slope. So you'd expect something like this, right? You'd expect sort of like a line just changing slope, but instead you get a straight line just translating in space, which is not clear at all. Why is that? Well, why is this? Think about, when is this phase 0? This phase is 0 when omega is equal to 0. Well, when is omega equal to 0? Well, we know that lambda, the wavelength, is equal to 2 pi times c divided by omega. So when this phase is 0 is when omega is equal to 0. Well, omega equal to 0, if you plug that into this equation, that's when lambda is equal to infinity. So therefore, this phase is 0 at infinity. So therefore, the anchor point of this thing is at infinity, and so what's happening is you are changing. This is clearly linear, so you are changing the slope. It's just that what's happening is it's kind of anchored at infinity, and you're sort of changing it like this, sort of like a windshield wiper. And we're zooming in on just this small little part, so it looks like you can't even see the difference. The slope is so insignificant that you can't even see it, and the reason is because at infinity there's a blue dot sitting at time 0 and not moving, right? So you can imagine it's sort of like this right now, or like this. And what's happening is it's slowly just going across like this, like a windshield wiper. And that's what's happening. So what's happening is when we did the Taylor expansion about 0, that caused the anchor point, the fulcrum of this linear slope, to be centered at infinity. So at infinity, it's doing this, and it's just sort of just doing this. And we're zooming in on such a small part that it looks like it's just a straight line translating in space. So that's not that useful, right? Because we want to see what the phase we're applying. We really want this linear thing because that's what we know. So let's try the other one. Well, the other one is this. This is when we centered it at omega naught, and we do get what we want. We do get this nice, okay, we have a nice line that's changing slope. That's what we want. And why is this? Why does it look good now? Because notice this phase is 0 when omega is equal to omega naught. If omega is equal to omega naught, this is 0, so the phase is 0. So what is omega naught? Omega naught is the central angular frequency. If you put that into wavelength, that's the central wavelength, or lambda naught. Lambda naught in this case is 800 nanometers. So you can see at 800 nanometers, the phase is always 0 because this is always 0. Everything cancels and the phase is always 0. And so it's just sitting here. So the fulcrum is now at omega naught. And you can see you have the linear phase. So an intuitive thing is, okay, the fulcrum of this linear phase is dependent on what we take our Taylor expansion about. So what point we take our Taylor expansion about determines the fulcrum here. So if we have omega minus omega naught, the fulcrum is going to be at omega naught. If we had 940 nanometers, converted that into angular frequency and did omega minus that, the fulcrum would be up here then, and it would change like this. So where you take the Taylor expansion of the phase determines the fulcrum in terms of where the phase is always 0, basically. So now we have this, and let's be honest with ourselves, this representation is much better because we can clearly see what we're applying, and it's very nice and pretty to see on a display, and it's with respect to the center of our spectrum, which is a very natural place to put it because we want to see what we're doing. So from now on, we're definitely going to take this Taylor expansion, the one that is about omega naught. We're not going to mess with that one that's with respect to 0 unless otherwise mentioned. So all these phase spectrum from now on are going to be with respect to omega naught. It's going to be with respect to the center of our spectrum. So we're going to have this Taylor expansion. So now we're talking about linear phase, and we want to see what linear phase did. I already showed you a picture of it, right? It looks like this, right? If you have it in terms of omega naught, it looks like this. But what does it do to the pulse? Adding a linear phase shifts the pulse in time. And it's not a very intuitive thing to say, but it's actually one of the first things I found extremely interesting when taking this representation and seeing what we could do, what we could talk about in terms of the phase. Adding the linear phase shifts the pulse in time. And that's the most interesting part, and I want to give an explanation using the representation that I introduced in video 1. And so the reason for that is, so here's the representation. I have a transform-loaded pulse, and you remember these blue dots represent the peaks of each wave. And so what I did is, notice one of these ridges later on, I put a line going through so you can see the slope of it. And I actually explained in video 1 why you have these ridges that get more sloped as you go out. And so I just put a line through one of these ridges. And let's forget about linear phase for a second and just think, what would you have to do to shift the pulse to this point in time? Right? What would we have to do? Well, clearly, what defines having a pulse at some point in time? Well, this is a transform-limited pulse, right? So if all the waves are aligned at that point in time, then the pulse would be centered there. So the new question becomes, if we wanted to shift a pulse to this point in time, what would we have to do to get all of the waves to align at this point in time? Well, clearly they're aligned like this right now. So to get them straight up and down, we'd have to shift these ones to the left a little bit, these ones a little bit to the left. These ones in the middle are perfect. They're straight up and down where we want them. And then these ones down here need to be shifted to the right a little bit. These ones need to be shifted way to the right. So if you want them to be if you want the waves to be perfectly aligned at this point in time, you can think that you'd actually need to apply the mirror image phase spectrum of this line. Why? Because it's in the opposite direction, and it's a mirror image, but it's the same magnitude. So it's kind of going to cancel its displacement from 0. If we call this 0, if we apply this phase spectrum, it kind of cancels out the local phase, so to speak, right? So what you can do is you can kind of picture each point in time gets its own phase spectrum, and this one at this point in time has this phase. It's just the slope of the ridge at that point. So if we apply this phase spectrum, we'd expect, if you kind of turn your head, this is almost like the negative function of this local phase, and they'll cancel, and the pulse will be shifted to that point in time. So let's try it. That's our hypothesis. If we apply the mirror image of this line, we should shift the pulse to that point in time. And let's test it. So here, I've left the lines. You can see that these are mirror images. I did apply the mirror image phase spectrum, and all of the waves are aligned at that point in time. So it's true, right? Applying the mirror image of the slope of this ridge shifted the pulse to that point in time. And this is actually a kind of one of the most interesting things, I think, part of this is that you can assign each point in time its own phase spectrum. So you can say at this point in time, the phase spectrum is like this. And if you applied the mirror image of that, the two functions will cancel and you'll get zero phase, which is transform limited pulse at that point. And so notice how it's all one-to-one too. You go from 0 and you get more and more sloped as you go out. So whatever linear phase I apply, there is some ridge somewhere that has that slope that's going to cancel out, and it's going to get 0 at that point. So for example, let's say I apply this phase spectrum. If I apply this phase spectrum, all I have to do is find the ridge that has this slope, because at that point we know that they'll cancel and you'll get a straight up and down line at that point in time. So this is why applying a linear phase shifts the pulse in time. It's because the slope of these ridges, I mean the line going through these ridges is a line. So the mirror image of that is also a line. So that's why adding a linear phase shifts the pulse in time. So you'd expect if you apply a linear phase that looks like this, you'd shift this way in time. But if you applied this linear phase, you'd shift that way in time. So that's why adding a linear phase shifts the pulse in time. It's because of the ridges. And that's why I stressed so hard the ridges in video 1, is because they're extremely important. Because at first, they just showed you where the constructive interference is. Now they can actually show you what the linear phase would be, how much linear phase you'd have to apply to shift it to that point in time. So the ridges are extremely important, right? And so here's a little GIF showing that. I'm just applying a linear phase again with respect to omega naught, and you can see the pulse is just shifting in time. And notice a few things. One, when the line is straight up and down, that's where the pulse is. So here the line is straight up and down, there's the pulse, straight up and down, here's the pulse. And then whenever the kind of waves are facing you, that's when the lines are straight up and down, that's where the pulse is, because when a line is straight up and down, all of the waves are adding up, constructively interfering to make the pulse. And when a line is very sloped, like here, you can see it's very sloped right now, the electric field is 0 because the number of peaks and ridges kind of average out and you get 0. So the explanation, so in the first video we talked about the Fourier expansion. I can do the same thing here. So if you want a more equation-based explanation, we can do the same thing. So we know the Fourier transform looks like this. So we have all this garbage, but we have e to the I omega t minus I phi of omega. If we're applying a linear phase, what is that? Well, we can say linear phase is just alpha omega is equal to, phi of omega is equal to alpha omega. So you can just plug that in to this equation and see what we get. If we do that, we get e to the e omega times everything the exact same, and we just replace phi of omega with alpha omega. And now notice here you have an I of omega in both terms, so you can factor it out, and you get the exact same thing up here, except you get e to the I omega times t minus alpha. Now this actually should be a little intuitive, because if you remember from like back in algebra, when you wanted to shift a parabola left or right, let's say you wanted to shift x squared to one direction, you just replace x squared with x minus some constant, so you replace x squared with x minus a squared, and that would shift the graph of the function by a. This is the same thing here. You shift this whole function in time by alpha, and alpha is the slope of our phase spectrum, right? So the slope, the more sloped you are, the harder it shifts in time, because you can shift the function left and right. And since the x-axis is in time, you're shifting the function left and right in time. So that's an explanation. But notice one thing. I kind of deceived you here. This is not omega minus omega 0. This is just omega. So this kind of gives an explanation as to why, for the Taylor expansion of the phase, about 0 would actually do the same thing. So if you applied a linear phase when we did the Taylor expansion about 0, it would also shift it in time. And this is the explanation for why that happens. This doesn't explain why adding a linear phase when you do a Taylor expansion about omega naught shifts the pulse in time. So that was a little trickery here, because this is omega, not omega minus omega 0. So that's sort of the explanation. An idea, if you do the linear phase for the Taylor expansion about 0, it looks like this, just the linear phase. I showed that earlier, and you can see clearly the pulse is shifting in time. And this is the explanation for that. So the explanation before using the slopes of the ridges was for omega naught. Here, I'm doing the explanation for 0. So adding a linear phase with the omega naught Taylor expansion and the 0 Taylor expansion shifts the pulse in time. And here's the explanation for that. Now let's talk about chirp. So now we're going to talk about the second order, right? So we talked about the 0th order. We know that that just shifts the phase of the waves within the pulse. We know that adding a linear phase shifts the pulse in time. Now let's see what the second order does. Okay? So we have the second order here, and we're just going to apply it, and here's what it looks like. So this part shouldn't surprise you at all as to why it looks like a parabola. A parabola, second order, we're adding second order. Clearly this is what's happening. But the pulse does something interesting. It stretches in time. You see as you apply more chirp like this, it stretches in time. Now why is that? And to explain it, I'm going to take a few screenshots. So here's the transform limited case. I'm aware it's a little blurry on the camera, but here we have a transform limited pulse. You can see all the waves are aligning at time 0, and you add up to a constructive interference, and you get a huge spike, and you have your pulse. Now when we apply chirp, you get this, and notice how it stretches in time. Why is that? Well, first let's talk about why does it decrease in intensity at 0. So at 0, you have all the waves aligning, and you add up to a huge electric field. Then you apply your chirp, and you get a huge decrease in electric field. Why is that? Well, notice how you no longer have all your waves aligned at time 0. That's an easy explanation. You no longer have all of your waves adding up. Some of your waves are shifted away, and so you're obviously going to get some addition from your neighbors, but also some troughs adding up, and you're going to lead to a decrease in electric field. But you're not going to go to 0. You're not going to go to 0 because notice how at the 0, at the very center of our spectrum, you still have these waves that are being added up. And we know that the center of our spectrum is actually the most important because they have the most amplitude. These top and bottom waves, we don't really care about them because they're not wavy at all. They have almost no amplitude. The ones in the middle contribute a lot to the pulse. And notice how the ones in the very dead center are still aligned, right? So you still get some constructive interference. It does actually bend away, but they're all pretty much aligned right in this kind of small region. And so you do get some electric field. So that's why you get the decrease, right? Because not all of the waves are aligned, but still some of them are. And so you get a measly, half the electric field that you had before or whatever. But a more interesting question is why does some point down here, let's look at this point. This is for a transform limited pulse. This is for a chirp pulse. Notice how you get a huge spike in electric field. That's a little bit curious, right? Why is that? Well, let's look at this ridge here. So we have some ridge that's sloped like this. When we apply second order phase, right, notice how this, I'm going to kind of shift it over here. Notice how the slope of this ridge is kind of beginning to align with the slope of the phase spectrum of its neighbors, right? So you have this ridge sending its top and bottom waves out in time. And you have this ridge who once was pretty close to 0 because the peaks and the troughs kind of canceled out. But now you have more peaks coming in from your neighbors. So the neighbors are kind of sending their peaks to you, so to speak, and you're getting this constructive interference back again because this slope kind of matches the slope of the ridge at this point in time, and you get constructive interference again, and that's why you add them back up. So when it was back here, you just had this linear thing, and what's happening is the number of peaks and troughs at any point in time kind of cancel out. But when you apply the second order phase, you notice how the slope at some ridge kind of matches the slope of the peaks of the ridge that sent its waves over, so to speak, and you get constructive interference back again. So that's kind of why you stretch the pulse in time, and you can expect the more curved this is, the further you send out your waves, the more peaks you'll reach, so to speak, and the more constructive interference further out in time you'll get. So that's why it stretches in time. But another curious thing is that if you're very receptive is the word, you can see this kind of red line going through the thing. I'm going to try to take it away. You can see this line kind of going through here. And it's not clear what that is, but you can kind of see this like linear thing going through the wave representation here. Now, what is that? Well, I'm going to kind of digress here and talk about another interesting thing about chirp. Chirp, yeah, it stretches the pulse in time. That's kind of interesting. But the big thing about chirp is that it does this. So here's kind of a caricature of it. What chirp does is it kind of has the high frequency components first, and then the lower frequency components later. So it kind of goes, or the other way around. So in this example, it kind of goes low frequency, and then it means oscillating faster and faster and faster to a higher frequency. Or if you applied the opposite, it goes high frequency, and then it kind of ends on a lower frequency. And this is what chirp does to a pulse in time. So you can't really see it up here because the difference is so astronomically small. If I remember correctly, this should be kind of the higher frequency, and this should be the low frequency. But you can't even tell. But that's just a graphical issue. It is there. But if you kind of blow up that effect, it would look like this. Except in this one, it would be flipped. But kind of a low frequency, and then oscillates faster and faster and faster, or the other way around, depending on whether you do this or this. So why is that? So that's actually the thing that people really care about when you talk about chirp. And this actually kind of shows why that is, this line. Let's think about this for a second. What is this line really what is your eye following when you see this line? Well, it's kind of following the point at which these ridges aren't really sloped when they're kind of straight up and down, right? This is kind of following the point at which all of the waves are kind of aligned at that point in time. So here all of the peaks are aligned, and then up here all of the peaks are aligned, and then everywhere that's not here, you can see that they're really like, it's this really dark here because they're very close together. And that's what your line is sort of following. You can see this linear thing, and notice how it's going from a short wavelength to a long wavelength. And put the line back up again. It's kind of going from a shorter wavelength or a higher frequency to a lower frequency. And so if just offhand here, if you were to add up the waves at this point in time, you seriously would get a huge amount of contribution from the higher frequency components, but not so much from the lower frequency components, right? Because you remember it's long wavelength to short wavelength. So the shorter wavelengths here would contribute a lot to the pulse. So you'd expect that the pulse here would be very high frequency. But over here, notice how if you were to add up all of the waves at this point in time, the longer wavelengths would contribute more because it's higher up, right? Because it goes from short wavelength to high wavelength, long wavelength, sorry. So then at this point in time, the longer wavelengths are going to contribute more to the pulse. And so you'd expect the pulse to have a longer wavelength here. And since this is linear, you'd expect this to go from high frequency linearly to a lower frequency. And so this is the straight line, and that's why they sometimes call this linear chirp, because the frequency in time is linear. You're going from, in this case, high frequency to low frequency linearly. So the pulse goes from high frequency to low frequency. Again, you can't really see it here, but it is there. And this is actually the valuable thing about chirp. Now, that's the explanation, but why does it do this? Why does it have this linear line through here? That's not exactly clear, but you can actually see this if you're willing to do some visualization. So if you have some ridge here, and you apply a second order curve like this, so you have this, and then you're adding it to this. So you have these two things that you're adding up. You have this straight line, and you have this curved thing. And I actually have a Desmos thing that shows this. So you have, let's say, okay, I'll switch it up here. So let's say that you have some ridge that looks like this, right? So some ridge that has a straight line, and then you're adding this phase spectrum on top of it. And so remember, when I was talking about linear phase, I talked about how you can have a local phase. So you can say that you have this local phase at some ridge that's sloped like this, really sloped clearly, and then you're adding this linear phase on top of it. And what does the net look like? Well, if you add these two together, you get a parabola that looks like this. So just to recap, the green is the slope of the ridge, the red is the phase spectrum that we're applying, and when you add them up, you get this net parabola. Now notice how this net parabola is kind of shifted up a little bit, right? And the reason that is, it's because it's when the slope of this added phase spectrum matches the slope of the ridge at that point, and that's when you get this zero slope here. That's when all the waves add up. So let me go back here. So you have let's say here, you have the slope of some ridge, and you're applying this phase spectrum to that point in time. Notice how towards the bottom, at the kind of bottom part here, that's when the slope of this kind of matches the opposite slope of the added phase spectrum, and that's when the slopes cancel. So the slopes cancel towards the bottom, right? When the ridge looks like this, the slopes cancel towards the bottom, and you get at the shorter wavelengths, that's when the slope is zero, and that's when the waves are adding up. That's when the waves are aligned, right? It's kind of a rough explanation, but then over here, again, if you had a ridge that looks like this, and then you apply the same phase spectrum, it's towards the top when the slopes cancel, when this slope matches this slope, and they cancel out, and you get zero towards the top. So that's kind of why it's due to the ridges, right? The ridges are sloped like this, and then they're sloped like this, and that's why when you add this phase to this phase, it goes to zero slope at the bottom, but when you have this phase added to this phase, the slopes cancel out towards the top. So that's sort of one explanation. It's a little bit hard to explain, but that's why you have this linear line going through, and clearly when you have a bunch of shorter wavelengths adding up to make your pulse, the pulse will be a shorter wavelength. So that's that. Another explanation which my professor uses, which is actually much better if you understand linear phase, is that imagine you had some phase spectrum that looks like this. Well, what you can do is you can just break it up. You can just say, at this point in time, these frequencies have a linear phase that looks like this. So they get shifted in time, right? We know that a linear phase shifts a pulse in time, so we can say that these wavelengths get shifted in time. the ones here don't get shifted in time because that's 0 linear phase. And then these ones get shifted in time the other way. So this is actually a very good explanation as to why, okay, your 750s come, let's say these come first, and then these stay in where at time 0, so to speak, and then your 900s or whatever come later. So this, since you can break this second order curve up into these linear lines, you can say, oh, the frequencies get shifted here, here, then here. And this sort of shows why these ones will get shifted very far in time, and these ones will get shifted very far in time the other way. And that sort of shows why, you know, a longer wavelength will come first, then a shorter wavelength or something like that. And you can actually extend this idea to any phase spectrum. You can take a third order, a eighth order, or whatever, and you can break them up into linear lines and say, oh, the wavelength will look like this, or the frequency in time will look like this because these wavelengths get shifted far backwards in time, let's say, and these ones get shifted forward in time, so it goes from shorter wavelength to longer wavelength, for example. So that's a good explanation for chirp. So that's been the video. That's sort of an introduction into the phase. I didn't talk about third order or fourth order or so on because you can really just plot the wave representation and see it, or you can use the linear lines to see what the frequency of time would look like, and you can just extend it from there. But I definitely invite you to watch the other videos. Feel free to share this. It's also no problem. But that has been the video. In the next video, I hope to talk more about intensity spectrums instead of phase. I know this was like kind of overloading you with phase. But in the next video, I want to talk more about intensity spectrums and see how can you use this representation to talk more about bandwidth and pulse duration, things like that. But that's been that. I appreciate you watching, and I hope to see you in the next video.